Welcome back, AP Stats students. So today we're going to work through section 6.1 in the textbook. And in chapter 6, we're starting the whole new unit, unit 3, Roman numeral number 3, on the topic of probability. So there's 4 chapters in this unit, chapters 6, 7, 8, and 9. And so 6.1 introduces us to the idea of randomness and probability. And specifically, the big topic in this section is simulation and how to run a simulation. There's 3 sections in this chapter. So in section 6.2, we'll look at probability models, and in section 6.3, we'll go over the general rules of probability. So again, the big idea here is that you'll be able to design and perform simulations to simulate some chance process. And we'll also describe the idea of probability and describe some of the myths about randomness. So the main idea of probability is based on the law of large numbers, which says that if you watch some chance process over and over again in the long run, the proportion of times that a specific outcome occurs approaches a singular value. That singular value is called the long-term relative frequency of that particular outcome. So just to define probability, probability is a number between 0 and 1, and it includes 0 and it includes 1. So if some process has a probability equal to 0, that means it will never occur. That particular outcome will never occur. But if an outcome has a probability of 1, that means that it always occurs. So most probabilities are between those two numbers, and they're expressed as a decimal between 0 and 1. So like 0.5, 0.25, 0.03, things like that. Okay, so the first, and this is a very powerful visual, and I encourage you to draw this visual in your notes. If you were to flip a coin, and when we're flipping a coin in AP statistics, we're always assuming that it is a fair coin, and we assume that there are only 2 outcomes, either a head or a tail. So the coin is not going to, land on its edge where it's, neither a head nor a tail. Okay, so there's an equal probability of heads and equal probability of tails. And each one of those long run relative frequencies, or each one of those probabilities, is 0.5. Okay, so in the short run, when you flip the coin, and if we want to choose the probability of one particular outcome, not the probability of both, probability of heads and a tail, because obviously that's, you're always going to get a head or a tail. So if we want to isolate one of those, and we'll just look at the probability of flipping a coin and getting a head. Okay, so in the short run, you can see that we have, this is the number of tosses on the x-axis. The long run relative frequency, what happens is, you get some heads and you get some tails, and you get some more heads, some tails, you get a whole bunch of heads, some tails. So what happens is, in the long run, this is going to even out, and it's going to even out at the true long run relative frequency, which is 0.5. But in the short run, there's going to be all this variability, all of this variation to the frequency or the relative frequency of the proportion of heads that comes out. Okay, so this is a very important visual to understand the long run relative frequency. Okay, so here's a few myths about randomness. And basically the big idea is that, like, probability, it is something that is, somewhat predictable in the long run, but we cannot make predictions in the short run. Okay, so the myth of short run regularity. Our idea of probability is that randomness is predictable in the long run, but it is not predictable in the short run. Okay, so we cannot make short run predictions. There's also this thing called the law of averages, which is also a myth. Probability tells us random behavior evens out in the long run. Future outcomes are not affected by past behavior. That is, past outcomes do not influence the likelihood of individual outcomes occurring in the future. So, an idea of like an example of the law of averages is if you go to the casinos, and if you go into a casino and you go to the roulette table, and with the roulette table, there are two outcomes possible. Either the roulette ball, when the table is spun, the roulette ball ends up in red or it ends up on a black. Okay. And so what they do is they post like the previous outcomes. And a lot of people that are betting in the casino will look at the previous outcomes and they'll say, I see there was a whole bunch of red that showed up in the past spins. And so that means that now, obviously, because of the quote unquote law of averages, the next outcome is probably going to be black. Well, that is not true. Okay, that is not true. And there's a whole concept called independence, mathematical independence, which basically disproves this law of averages. So now we get to what is called a simulation. So a simulation is basically you're just imitating this chance behavior. Okay, and simulation is extremely powerful because it is a much safer, much easier, more efficient, less expensive way of figuring out what is going to happen, what is likely going to happen with some chance process. Okay, so we simulate it rather than actually doing whatever the chance process is many times. You can simulate it over and over and over again very quickly, especially if you're using computer software or a calculator or something like that. You can do many, many, many different iterations of this simulation very quickly. Okay, so state plan do conclude is the process we want to use again for performing a simulation. Now, in our textbook, they actually do not use this four-step process. They use more of a five-step process. But the only difference between our textbook's five-step process and this four-step state plan do and conclude process is that with the plan, you're also going to state assumptions that are within there. Okay, you're doing what our textbook calls stating assumptions. Okay, that is all part of the planning process. Okay, so we want to state very clearly, we want to isolate what is the chance or what is the question of interest. Okay, and then we want to plan out like how are we going to simulate? How are we going to run our simulation? What kind of technology are we going to use? And we also want to assign in advance of doing the simulation, we want to assign what the outcomes of the chance process are and what variables we're measuring. Okay, so we want to state all of that upfront before we run the simulation. Then we're actually going to do the simulation and we're going to perform many repetitions of the simulation. And then we analyze the data that we gather and we use the results of the simulation to answer the question of interest. Okay, and so when we're running a simulation of a chance process, we're going to be using table B, okay, the table of random digits, and or technology, okay, and or our calculators. So here's an example from page 396 in our textbook. And it's about a couple that plans to have children, and they're going to stop and they're going to keep having children until they have their first girl. Okay, or until they have four boys. Okay, whichever comes first, that is when they're going to stop. So if they have a girl on their first child, they're going to stop. And if they, have a boy, then they're going to have another child. If that's a boy, they're going to keep going, obviously, until they have their first girl or until they have four boys in a row. Okay, so we're going to design a simulation using table B. Okay, and so when we're designing the simulation, we're going to use the state plan do conclude. State is we'll simulate this couple's outcomes for having children until they have a girl or until they have four children, whichever comes first. Okay, when we plan, we're going to use table B and we're going to start on line. You choose a line, it doesn't matter. Okay, choose your own line. And I want you to actually do this right now as you're listening to this video. Turn to the back of your textbook and choose a line, okay? And then we're going to read from left to right, reading one digit at a time, and we're going to define the digits 1, 2, 3, 4, 5 as being a girl, and the digits 6, 7, 8, 9, and 0 as being a boy. Okay, so stop when we have one girl or when we have 4 boys in a row, whichever comes first. Okay, we're also going to skip repeats. I didn't write that in there, but that's an important thing we need to include. We're going to skip repeats. Okay. 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 So now we go ahead and do the simulation, and let's do this simulation 10 times. Okay. Let me go ahead and grab my textbook, and I'm going to run my simulation 10 times. You guys run your own simulation. Okay. And I'm looking at table B. And I'm just going to make mine simple. I'm just going to start on line 101. Okay, line 101. Okay, so I'm going to read from left to right. Okay, and my first digit is a 1. That's a girl, so I'm done. Okay, so that's one simulation, but I'm going to repeat this process 10 times. Okay, so now I start from the very next digit. Okay, and so now this is the couple again. This is another simulation. Okay, so my first digit is a 9. That's a boy. Second digit is a 2. That's a girl. Okay, so now I stop. So my second simulation had the couple having 2 children. Okay, my third simulation. Okay, my very next digit is a 2. That's a girl. I stop. And then I go on and on and on, and I repeat this process 10 times. Okay, and I want you to do this 10 times and write down your results. Okay. So now we're going to conclude. So we believe that the long run relative frequency of having at least one girl in the first 4 children is what? Blank out of 10. How many times out of 10 did the couple end up having a girl? Okay, and not having 4 boys in a row. How many times did that happen? Well, for me, that happened 9 out of 10 times. Okay, so I believe I'm going to conclude based on my simulation that I believe that the long run relative frequency of having at least one girl in the first 4 children is 9 out of 10, or remember that probabilities are stated not as fractions, but probabilities are stated as decimals between 0 and 1. So I believe, based on my simulation, that the probability of having one girl in the first 4 children is 0.9. Now, what are the assumptions that I made? I made an assumption that the probability that the long run relative frequency of having a girl versus having a boy is equally probable at 0.5. Okay, that having a girl versus having a boy, the probability is 0.5. Okay, that's an assumption that I made. I also made an assumption that having children is what's called an independent event. It's called an independent event. What that means, independent simply means that whatever the outcome of the previous event was, or whatever the previous outcome was, it has no bearing or it has no impact on the probability of the next outcome. Okay, so the fact that this couple has a boy first, it doesn't change the long run relative frequency. It doesn't change the probability of having a boy or a girl the next time. It's still 0.5. It's like if you're flipping a coin. Okay, if you flip a coin and you end up with a tail the first time, okay, the next time you flip it, does that reduce the probability of getting a tail because you got a tail previously? No, it has no bearing. Okay, it has no impact on, it does not change the probability. So we consider that what is called an independent event. Here's our next example, and this is from the newer version of the textbook. So the golden ticket parking lottery, okay, simulation with table D. In the new book, this is called table D. In our book, this is table B as in boy. Okay, so at a local high school, 95 students have permission to park on campus. Each month, the student council holds a golden ticket parking lottery. Okay, so this is a high school, and only 95 passes are given to all the students. So that is not enough passes for all the students to park on campus. So they have to have a lottery. Okay. So each month, the student council holds a golden ticket parking lottery at a school assembly. The two lucky winners are given reserved parking spots next to the school's main entrance. Last month, the winning tickets were drawn by a student council member from the AP statistics class. When both golden tickets went to members of that same AP statistics class, some people thought the lottery had been rigged. There are 28 students in the AP statistics class, all of whom are eligible to park on campus. Design and carry out a simulation to decide whether it's plausible that the lottery was carried out fairly. Okay. So we're going to go ahead and design a simulation. So let's use the state plan do conclude model. Okay, state, what's the probability that a fair lottery would result in two winners from the AP statistics class? Okay, we'll use table B, not D, but B to simulate choosing the golden ticket lottery winners. Since there are 95 eligible students in the lottery, we'll label the students in the AP stats class from 0, 1 to 28 because there's 28 of them, right? And the remaining students from 29 to 95. So those are the other students that are not, not in the AP statistics class. So numbers 96 to 0, if we land on those, we're just going to skip them. Okay, moving left to right across the row, we'll look at pairs of digits until we come across two different labels or two unique labels from 0, 1 to 95. The two students with these labels will win the prime parking spaces. We will record whether both winners are members of the AP statistics class, yes or no. Okay, so now let's do the do. Let's perform many repetitions of the simulation. We'll use table B starting at line 139. The digits from that row are shown below. Okay, and just wait for the next slide. Okay, we have drawn vertical bars to separate the pairs of digits, and underneath each pair, we have marked a check mark if the chosen student is in the AP Stats class, an X if the student is not in the AP Stats class, and skip if the number is not between 0, 1 and 95, or if that student was already selected. So notice that we're skipping repeats. Note that if the consecutive 70 labels had been in the same repetition, we would have skipped the second one. Okay. So here we go, reading across. Okay, so AP Stats students are 0, 1 to 28. All the other students are 29 to 95. And we're going to skip these if we have digits 96 through 00. Okay, so reading across row 139 in table B, look at pairs of digits until you see two different labels from 0, 1 to 95. Record whether or not both winners are members of the AP Stats class. Okay, so here we have 55 and 58. That's not in AP Stats, not in AP Stats, so that's a no. 89 and 94, that's a no and a no, so that's a no. 4 and 70, that's a yes from AP Stats, but that's a no, not in AP Stats, so overall that's a no. So 70 and 84, that's a no. So 10 and then 98 is a skip because that's outside of the range, and then 43, so that's a no. So that's an AP Stats and a non-AP Stats. This is a no, no, no. This is still a no because that's yes in AP Stats, but not in AP Stats. Okay. This is a yes, AP Stats and AP Stats. No, 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 yes, no, yes. Okay, so how many times did we do this? We did this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we did this 20 times. Okay, sorry, 9. So we did this 18 times. And how many times did we get both people from AP Stats class? 3, right here, and right here. So we had 3 successes out of 18 trials, right? And so what is that estimated probability. So our probability for our simulation is 3 out of 18, or 16.67. So this is an estimate of the long run relative frequency. Okay, it's an estimate. Okay, so really what we're doing is, you see, we only did this 18 times, but if we did this 28 times, okay, or if we did this 58 times, or if we did this 108 times, or let's say we did this with a computer and we made the computer do this 1,000,000 times, okay, if we did it on a computer and we simulated this and we did 1,000,000 repetitions, we would probably get a very reliable number, a very reliable estimate of the long run relative frequency. Okay, what the true proportion is of getting 2 students from the AP Stats class, right? Since we only did it 18 times, we have an estimate of what we think is the long run relative frequency, but we know in the back of our mind, we're like, yeah, there's probably a little bit of error in this. Okay, but this is good enough. This is our estimate. Okay. Okay, so that is how you perform a simulation. You're going to follow the state plan do conclude. You're going to use table B. Okay, and you're going to explain how you use table B. You're going to label. You're going to explain very clearly what the labels are. Okay, what we consider a success, what we consider a not success. And then we're going to do the simulation, and we're going to do many repetitions of the simulation. And then what we're going to conclude with is, we're going to conclude with some relative frequency that we believe to be an estimate of the true long-term relative frequency of whatever chance process we are describing. Okay. All right, guys, that's all I have. I will see you in the next lesson.